So in 8.3, we have two different aims. Our first aim is to understand the mole concept and Avogadro's number. And the second aim is to learn to convert among moles, mass, and number of atoms in a given sample. If you have done well with conversion up to this point, this is just introducing another equivalent statement, which turns into another conversion factor for you. If conversion factors and dimensional analysis problems are something you've struggled with in the past, now is the time to seek extra help, because the rest of the year for us is going to be based on this idea of conversions and using the mole. So what we need to talk about first is what the mole is. And in order to introduce the mole, we need to talk about just a few simple concepts and vocab terms that you're already familiar with. For example, if I have 12 eggs, what would we call that? We would call 12 eggs a dozen. Everybody know that 12 eggs is a dozen eggs. 24 eggs, we could then say, is 2 dozen eggs. And then most people don't know what 144 eggs is called, but this would be called a gross of eggs, a dozen. It's just a way to express the amount in a group, and that's it. That's all a mole is. Numerically speaking, if I had 6.022 times 10 to the 23rd eggs, I would have a mole of eggs. So just like a dozen represents 12, in each of these cases, a dozen represents 12, except a gross represents 144 here. But in this case, a mole, which is just another word for a specific amount, just like a dozen and a gross are. A mole is 6.022 times 10 to the 23rd. So I could just say a dozen equals 12, a gross equals 144, 1 mole equals 6.022 times 10 to the 23rd. Remember, we talked about atoms being so small. So we need the mole to be able to tell us how many atoms we have without counting individually. We're going back to this idea of counting by weighing. If I have 12 carbon atoms, how many carbon atoms do I have? We can call that a dozen, because 12 just means a dozen. If I have 24 carbon atoms, I have 2 dozen carbon atoms. If I have 144 carbon atoms, I have a gross of carbon atoms. Notice this part is not changing. The dozen, the gross, that reflects the number, not what it is that I'm talking about. So I can change that unit to whatever I want. A dozen people is 12 people. A dozen chairs is 12 chairs. It doesn't matter. All that matters is that I have the correct number to reflect the correct unit. So if I'm talking about 6.022 times 10 to the 23rd carbon atoms, I now have 1 mole of carbon atoms. So here's the fun part. If you look at your periodic table, how much does 1 mole of carbon atoms weigh? Look at the mass of carbon from the periodic table. The mass of carbon is 12.01 grams. So this is the number of grams in 1 mole of carbon atoms. If I wanted to tie a specific number to the individual carbon atoms, remember a mole represents the group, but if I wanted to say how many individual atoms are in 12.01 grams of carbon, this is how many atoms are in 12.01 grams of carbon. So I can just make this a string of conversion factors. 12.01 grams of carbon equals 1 mole, and this equals 6.022 times 10 to the 23rd atoms. And now I could string these together in any way that I wanted to. I can convert grams to moles. I can convert grams to atoms if I wanted to. So these conversion factors just allow us to figure out maybe how many atoms I have in a certain mass of a sample. It allows me to figure out how many moles of a sample I have. It allows me to figure out the mass of a sample based on the number of atoms. So this just allows us to go back and forth and to be able to use the mole as a bridge between that very large number that represents atoms and the number that we see on the periodic table. Or to put into words, we could say the mole, and notice the abbreviation of mole is the same just without that E. A mole is a sample of an element with a mass equal to that element's average atomic mass, expressed in grams, and that contains 1 mole of atoms. All that means is, look at the periodic table. Average atomic mass is that number that's on the periodic table, and we talked about how to calculate that in the last section. So for carbon, the average atomic mass is 12.01. We can use that number to refer to just one atom, or we can refer to that number in terms of grams if we're representing 1 mole of atoms. And we talked about how many a mole was. So the next step in talking about the mole is we have this equivalent statement. How do we plug that into a dimensional analysis problem? And what types of problems will be asked of me to know I have to use that? Looking at lithium, for example, if we look at the periodic table, we can see that the mass of lithium from the periodic table is 6.94 grams. Now, this is equal to 1 mole of lithium atoms, just like we said with the example of carbon that we just talked about. This is equal to 6.022 times 10 to the 23rd lithium atoms. 4 grams of helium, based on the periodic table, is equal to 1 mole of helium atoms, which is equal to 6.022 times 10 to the 23rd individual helium atoms. So I need to know whether I'm talking about the group or each individual atoms. If I'm being asked how many atoms are in this sample, then I want to use that number, Avogadro's number, the 6.022 times 10 to the 23rd. If I'm being asked how many moles of atoms are in this sample, this size mass of this sample, then I'm just going to go to moles. So either way, I've got a bunch of conversion factors to choose from. If I'm looking at 8 grams of helium, you don't even have to do much of a calculation here to determine what the answer is, because we know that 4 grams of helium was 1 mole, therefore 8 grams of helium are 2 moles of helium atoms. How many individual atoms is that? Twice Avogadro's number, 2 times 6.022 times 10 to the 23rd helium atoms. Remember, if you are being asked to calculate something very tiny, like an atom or a molecule, that's when you need to use Avogadro's number, because we need a very, very large amount of things that are so tiny. For our sample problem, we're asking how many atoms of hydrogen are in a 5-gram sample of hydrogen. So look at the question. It's asking how many atoms. And if I'm talking about a 5-gram sample, I know that's going to be a pretty large sample. And if I have a pretty large sample, something I could hold in my hand would be 5 grams. If I have a 5-gram sample of something, I know there has to be a lot of atoms in there. So if we're contextualizing it in that way, we can see that a sample that's big enough that I can hold in my hand would need a very large number, which means I need to use Avogadro's number here. Now, if I'm starting with 5 grams of hydrogen because this is my given piece of information, then I'm going to follow through with this process the same that I would any type of dimensional analysis problem. I'm going to put grams of hydrogen on the bottom because I know those two values will cancel out. If I have one on the top and one on the bottom, those units will end up canceling. What I'm going to are moles, and I know that number on the periodic table allows me to go from grams to moles. That is the number of grams per mole. So we may see on the periodic table something, or in a given piece of information, something that looks like this. 1.01 grams per mole, and that's what that means. This is grams per mole. Doesn't always have to be grams on the top and moles on the bottom. Remember, we're just using this to be able to convert from one unit to another. Now, can I stop converting at this point? I can't, because the question that was asked of me was how many atoms of hydrogen, and I'm in moles of atoms right now, so I need to get down to that very large number. So my last step is to put moles of hydrogen on the bottom, and then Avogadro's number of hydrogen atoms on top. So when I put this in my calculator, this is where you have to be careful, and you have to practice putting these in your calculator to make sure that you're doing this correctly, especially if Avogadro's number ends up being on the bottom, because you want to make sure that that value is in parentheses. So on top, I'm going to multiply 5.0 and then in parentheses 6.022 times 10 to the 23rd. And when you put this in your calculator, depending on what type of calculator you have is going to determine how you enter it. You could do 6.022 times 10, and there's a caret button on your calculator that looks like that. So you'll type 10 23rd. You can also say 6.022, and on certain calculators, certain TI versions of the calculator, you might see a button that looks like this, and you would put that and then 23. However you decide to put it in is fine. But like I said, especially if that number is in the denominator, make sure you have it in parentheses. When we put this in the calculator, we get 2.981 times 10 to the 24th hydrogen atoms. So we always want to ask ourselves, does this answer make sense? And we see that that 10 to the 24th means that, yes, that is a huge number. We expected it to be a huge number because if it is a 5-gram sample, that's a lot of hydrogen in this case. And if it's a lot of hydrogen, I expect there to be a lot of atoms in that sample. And 10 to the 24th atoms is a lot. So yes, we did come up with an answer that makes sense. Next problem, calculate the number of moles of atoms in 10 grams of aluminum. So now we want to be able to identify aluminum on the periodic table. It's in the third row, that first element of the P block, element number 13. So we can see that aluminum has a molar mass of 26.98 grams per mole. We say molar mass because it's the number of moles, 1 mole in a certain number of mass. So we call that molar mass. So calculate the number of moles of atoms. Notice here I am not being asked to calculate the number of atoms. So I'm not going to use Avogadro's number here. I will be using the mole. So I'm going to start with 10 grams of aluminum. If I start with 10 grams of aluminum, I'm going to draw my line. I know grams of aluminum have to go on the bottom because grams of aluminum have to cancel out. Notice I switched here between writing the name and writing the symbol. As you're converting, the symbol makes it a little bit easier and cleans up the writing in each of your individual conversion factors. So it's okay to change between the name and the symbol as long as you're sure that they match. So this 26.98 grams per mole, 26.98 grams on the bottom, 1 mole on top. So in this case, I can stop here because I was asked to calculate the number of moles of atoms, which means I'm multiplying 10 times 1 on top and then dividing that by 26.98 on the bottom. Remember, we can always ignore the ones. So really the math that you're doing here is 10 divided by 26.98. And this gives us 0.3706 moles of aluminum. Think about this number in terms of the math that we're doing. If 1 mole is 26.98 grams and I have 10 grams, I have just a little bit more than a third of the amount of grams required for 1 mole. And 0.37 is slightly more than a third. So this number does make sense in terms of the math that we're using. How many atoms is this? Now, this is taking this type of problem one step further. I calculated the number of moles, so that's what I'm going to use to start this next problem. This is now where we want to use Avogadro's number, because if it's asking for the number of atoms, I'm going to need a very large number to represent something so small. So I'm going to draw my line, 1 mole of aluminum on the bottom, and what's going to go on top is now Avogadro's number, 6.022 times 10 to the 23rd atoms. Notice I'm going to end up with slightly more than a third of a mole. And if I do this calculation, 0.3706 times 6.022 times 10 to the 23rd, put this number in your calculator, you end up with 2.232 times 10 to the 23rd aluminum atoms. A calculator is going to be very important in this chapter. So please make sure you have access to a calculator in one way or another. Your phone can act as a calculator. The library at school does have some calculators to be able to check out to you. If you have trouble, please contact your teacher and ask them if they can help you track down a calculator. But it is going to be very important in this chapter. In section 8.4, we've got 2 different aims. The first aim is to understand the definition of molar mass, which I did already mention in that last section, so you should be familiar with this already. And then to learn to convert between moles and mass of a given sample of a chemical compound, which we've really, again, already been doing. So we know how to do this already. This is just reiterating the concept one more time. So molar mass is the mass in 1 mole. And remember, this changes depending on which element that we're talking about. We are always talking about 1 mole of this compound. So that's how the mass is able to change. If we keep that mole idea the same for each element, then the mass is going to change based on each element's average atomic mass. Now, here we are looking at how to calculate molar mass for a compound. We know the molar mass of an individual hydrogen atom, and we know the molar mass of an individual oxygen atom. What we want to look at here is how to transform that into what molar mass would look like for a compound. And it is just as simple as adding them together, and that's it. So for hydrogen, we know an individual hydrogen atom has a molar mass of 1.01 grams per mole. The 2 comes from the formula right here. So that 2 tells us that we have 2 hydrogen in one formula unit of H2O. So 1.01 times 2 gives us a total contribution from hydrogen in this compound of 2.02. Oxygen. We know that that molar mass, based on the periodic table, is 16 grams per mole. There's only 1 in this formula. Remember, if there's nothing here, we have an implied 1. So 16 times 1 gives us 16. Now we just add these together. And when we add them together, we get 18.02. Remember, we need to specify the unit on this number. Numbers mean nothing without their units. So molar mass always has to be in units of grams per mole. So the unit for this number is 18.02 grams per mole, and this is specific to hydrogen. For the next one, we need to calculate the molar mass of this compound. See if you can take just a minute to name this compound. The name here is calcium carbonate. Now at this point, it doesn't really matter what ions are used to form this compound unless I'm asking you to do it from the name. But if you're asked to calculate the molar mass of calcium carbonate, or CaCO3, all you care about is the formula, because the formula tells you how many of each element you have. So we're looking at one formula unit, and then we're breaking it down by element and how many of each of those elements are in this formula. So for calcium, looking at the periodic table, this has a mass of 40.08 grams per mole. How many are in this formula? Just 1. So that 1 contributes 40.08. For carbon, 12.01 grams per mole. How many are in this formula? Again, just 1. And a lot of people will look at this and say 3, but remember the subscript, unless it's outside of parentheses, only applies to the element that it's immediately attached to. So 1 carbon atom is 12.01 grams per mole. Oxygen is 16. Now in this case, according to this formula, I have 3 oxygen atoms. And if I have 3 oxygen atoms, that's going to give me a total of 48. When I add these up together, I see that this is 100.09, again, grams per mole. And a lot of these, you'll find that the more you use them and the more you get used to calculating them, the more familiar you are with them, the less you actually have to calculate, because it does start becoming natural the more practice you do. So you could see calcium carbonate and just know that that's 100.09 if you end up practicing these problems enough. Calculate the number of moles in 1.56 grams of C10H6O3. So this problem is a little bit different. I'm asking you to do multiple steps here. I'm asking you to calculate the number of moles in 1.56 grams. Are we going to end up using Avogadro's number in this problem? No, because I am not asking you to calculate the number of atoms or the number of molecules. I'm asking you to calculate the number of moles, which represents that whole group. So we're going to start with what we've been given, 1.56 grams of C10H6O3. What we're going to put on the bottom is grams of C10H6O3. So I'm converting from grams to moles. What we have to do now is figure out this number. We need to figure out what goes right there. And how do we do that? We're going to take this compound, break it down, and calculate the molar mass. Carbon, we know each individual carbon atom is 12.01. We know there are 10 of them according to this formula. So that gives us a total of 120.1 grams per mole. Hydrogen, 1.01. There are 6 according to this formula. So that gives us a total of 6.06 grams per mole. And for oxygen, 16 times 3, which gives us a total of 48 grams per mole. So remember, these numbers are coming directly from the formula. So when I add all these together, I get a total of 174.16 grams per 1 mole of this compound. So now I've calculated the molar mass, and I'm just using the molar mass to be able to convert from grams to moles at this point. So when I've set up this problem, it's set up in a way that since the molar mass is on the bottom, I'm dividing 1.56 by 174.16 to get my answer. And here I get 0.008957. Is this my final answer? Not exactly. So I could represent sig figs here, but remember, we're not really looking at that. If you were representing sig figs, it would be just a little bit different, 0.00896. But what's more important than that is the unit in this case. So we need to remember to have the unit of our final answer. So I would accept 0.008957 moles of C10H6O3. So in the last section for today, we have one aim, and that aim is to learn to find the mass percent of an element in a given compound. If you understand what molar mass of a compound means from the last section, and if you understand what percent means, we are combining those two ideas together in the final section for today's notes. So mass percent, anytime you're talking about a percent, you're talking about the part over the whole, and mass percent is no different. The part is the mass of the element. The mass of the compound represents the whole. So I'm looking at just the mass the element takes up out of the mass of the entire compound. That's what mass percent represents. And don't forget to multiply it by 100 to represent that we have a percent. So if I'm asking you to find the percent composition of carbon, percent composition is the same thing as mass percent. I'm asking you to find the mass of carbon in C2H5OH. So the way to approach this is to first find the mass of the compound. And in finding the mass of the compound, you have to find the mass of the element anyway. So one step leads you to another, and you just take the parts of that and plug them into the overall problem. So let's take a look at what I mean by that. Start by calculating the molar mass of the whole compound. We know that carbon has a mass of 12.01 times 2, which gives me 24.02 grams per mole. Hydrogen, 1.01 times 6. So notice there are 5 here and 1 here for a total of 6. And that gives us 6.06 grams per mole. And then oxygen, 16 times 1 is 16 grams per mole. So you have to find the molar mass of this whole compound because you need to know what percent of that whole compound is carbon. And once we do this, we get a total molar mass of 46.08 grams per mole. So what we want to do is take the part, which is 24.02. Remember, this is your part. And we want to divide that by the whole. And the whole is 46.08 grams per mole. After multiplying by 100, we see that carbon makes up 52.127% of this compound.